Hello YouTube. This video examines the earthquake predictions made by the user known as the Barcaroler, who formulates his predictions based on his study and analysis of solar activity and upcoming planetary alignments. Now he doesn't claim that these events cause earthquakes, but he does claim that there's a correlation between these events and earthquakes. Now this sounds suspiciously like electric universe theory to me, but that's a topic for another time. A time that will not arrive. Now before we go too far, let me forewarn you that the introductory part of this video does get a bit lengthy, but I felt it was necessary to explain what I've done, how I've done it, and why. More to the point, I hope it will demonstrate that I've been very fair and very thorough, and I think you'll be somewhat surprised when we get to the final results. So let's jump back to the planetary alignments for just a moment. Now I've been a huge astronomy buff since the first grade, and to this day I maintain a very high interest in it. But I don't have some of the software that I needed for this part of the video. So on August 10th, 2014, at about 4:35 p.m. CDT, I got on Skype with my friend Dazza the cameraman down in New Zealand, and he generated these images for me so that I could use them in this video. And Dazza, once again, thank you. Back to the Barcaroler. In the first 12 videos in which he stated that a planetary alignment was in play, his alignment images look like this. In this particular image, he was pointing out the alignment between Neptune, Venus, and Saturn, shown by this line. But we have a series of problems here. If you know anything at all about astronomy, then you ought to know that the planets' orbits are not evenly spaced, and therefore this is not an accurate depiction of our solar system. Nor does it represent an alignment that even the Barcaroler himself was looking for. Further, in reality, the planets' orbits are not perfect circles, and they are not concentric, meaning they don't all have the same center point. Well, what does that mean? Well, most people might think that the center of the Sun is the center of the planets' orbits, but in reality that's not the case. So let's take a look at the first 4 planets just as an example, and we'll start by exaggerating the Sun just a bit so we don't lose sight of it. Here's Mercury's orbit, and notice how off-center it is from the Sun. And here's Venus's orbit, and notice that its center is in a different location. Here's Earth's orbit, and its center is in yet a third location, and then we have Mars, whose orbit center is way out here. And notice that the orbits are not perfect circles. They are oblong, some more so than others. This is called orbital eccentricity. So back to this alignment. This image came from a program called SimSolar, which is the program that the Barcaroler was using. Dazza was also using it when he and I were on Skype so that he could reproduce the Barcaroler's results. And when we click this checkbox in the upper right corner, it tells the program to show the orbits to scale, and there they are. And what happened? Well, there's no alignment, is there? In fact, it's off by quite a bit. Same date and time in both images, but in one image the orbits are evenly spaced, and in the other they're more to scale, and of course this changes the planet's orientations to one another. So as I said, the Barcaroler made this same mistake in the first 12 videos in which he stated that a planetary alignment was in play. Then he suddenly switched to a different program, one called Solar System Scope, which also shows the orbits evenly spaced as well as to scale, but unlike SimSolar, it also shows their eccentricity. So what happened? Why did he make this switch? Well, between the last video in which the Barcaroler used SimSolar and the first video in which he used Solar System Scope is when my friend Dazza came along and pointed out his error.
Thank you. Thank you very much. Thank you.
For those wondering, I met Dazza when I joined a discussion group on Facebook that he had founded called Vortex, Voices of Reason to Explain X. So at any rate, upon receiving Dazza's notification, the Barcaroler switched from SimSolar to Solar System Scope, and from that point forward, his solar system images, and therefore alignments, were actually accurate. And in this one, we see an alignment of Mars, Earth, and Mercury, shown by this line. So let's tip the solar system so that we're looking at it on edge. There we go, that's pretty close. Now let's add our line again, and we see that Mars, Earth, and Mercury are in alignment. Or are they? Let's do something else just to check. This image came from Starry Night Pro, another program that Dazza was using when he and I were on Skype. Like Solar System Scope, it shows the orbits to scale and their eccentricity, but it also allows us to view anything from anywhere. So DAZA told it to show us the view of this alignment as if we were actually standing on Mars. And, uh-oh, what's going on here? If Mars, Earth, and Mercury are in alignment, should we really be able to see Mercury? Shouldn't it be directly behind the Earth? In Solar System Scope we see that it is behind the Earth, but in Starry Night Pro it looks like it's way up here. It should be here, but it's up here. So what's going on? The answer lies in another property called orbital inclination, but in Solar System Scope, at this point in time, Mars, Earth, and Mercury are too far apart for us to zoom in enough to actually see it. But let's go back to Solar System Scope anyway and try something. Now at the moment I have the orbit set to circular and evenly spaced, but for right now that's okay. Now most people might think that all the planets orbit the Sun on the same plane, for example the plane that might pass through the Sun's equator. So let's turn the solar system on edge again, and you may have already noticed something the last time we did this. Okay, that's pretty close, so now I'm going to tell the program to show the orbits as they really are. And boom! What happened? Well, let's zoom in and take a look. I hope this is clear enough in the video, but do you see what's going on here? Look at Mercury's orbit, which is right here, and notice its angle. And then compare that to the angle of Venus's orbit, which is right here. And down here is the Earth's orbit. Now let's swing this around a bit, and we'll put Venus over on the far right. And then we'll line up Venus's orbit so that it crosses right in front of the Sun. And look where the Earth's orbit is. It's way down here, and if we line up the Earth's orbit in the same fashion, we see that Venus's orbit is way up here, and we can still see Mercury's orbit. It's this one right here, at this angle. So this is what we mean by orbital inclination. The orbit of each planet is at a different angle. Let's do a short recap. Not only do all planets' orbits possess their own degree of eccentricity, in other words, they're not perfect circles, and not only are their centers not the Sun, and not only are their centers in different locations around the Sun, but they also possess their own angle of inclination. So, as you can see, there can never really be an alignment. There can be if we view the solar system from above or below and assume that it's a two-dimensional object, but not when we change our vantage point in the reality of 3 dimensions. But that's okay. We'll assume that these are indeed alignments, and we'll look at the data anyway. After all, the Barr-Caroller identifies these as alignments in a two-dimensional universe, so we'll treat them as such. However, I am tossing the 12 videos in which the orbits were evenly spaced. After all, those predictions were based on alignments that never even occurred, and never could occur even if we do view the solar system from above or below. And besides, I wouldn't want the results to be skewed against his favor. Again, the goal is to be fair. So setting those videos aside, does his system work? Well, let's find out. Now, before we jump right into the analysis, we need to recognize a few things first. For example, it's not enough to examine earthquake activity that occurred within his prediction periods. We also need to examine earthquake activity that occurred outside his prediction periods. In addition, we also need to consider whether or not the probability of a particular size earthquake in a particular location is worthy. For example, if I predicted, say, a 6.0 earthquake or above in, say, a 4-day window, and if I predicted it to occur anywhere on Earth within those 4 days, then I would be right more than 85% of the time. Now, there's no such thing as a sure bet when it comes to predicting earthquakes, but a 6.0 or above occurs about every 2.5 days. So if I predicted one to occur in a 4-day window, it's just not a very impressive prediction. In other words, the probability is just too high. But the Barr-Caroller doesn't predict that an earthquake of X magnitude will occur anywhere on Earth within a specific period of time. Rather, he predicts that it will occur in a specific location, for example, Guam, or a specific area, like the Aleutian Islands. So to calculate the probabilities, not only do we need to know how many earthquakes there are, but we also need to know how many earthquakes there are of any specific magnitude and above, at every latitude and longitude combination. Now that might sound like a rather daunting task, but we can round the latitudes and longitudes to the nearest 10 degrees for the purpose of calculating probabilities. It's just not necessary to take them all the way down to degrees, minutes, and seconds, and besides, I'm not going to pin him down to within a few meters. That's a little over the top in my book, and as we continue through this portion of the video, I think you'll agree that I've been pretty darn fair to the guy. So to get this information, I went to the USGS website, the USGS being the United States Geological Survey. The USGS has a very large online database of earthquake activity covering the entire globe. And, of course, if I'm going to calculate frequencies and probabilities that are at least reasonably accurate, then I need a rather large set of data. But in looking at the USGS data, I saw very quickly that the data from the 70s and 80s is somewhat sporadic at best. But from 1990 forward, it's pretty solid. So that's what I downloaded. All earthquake data from January 1st, 1990 through June 30th, 2014. Basically, 24.5 years of earthquake data. In addition, one of the file formats they provide for download is CSV, or comma-separated values, which is native to Microsoft Excel. Well, that's pretty cool. That means we can open this downloaded data in Excel and look at it that way. It also means that it's just a plain flat ASCII text file, which can also be opened in Notepad. In addition, because it's a flat text file, it can be easily read and processed by a program, should you be inclined to sit down and write one. And that's what I did. In fact, I wrote several programs for this analysis. And since it wasn't possible to download all 24.5 years of data in a single session, I had to download it in pieces. Therefore, the first program I wrote was a program that simply concatenated those pieces into one large master file. And this is what that file looks like in Notepad. Not entirely convenient, but it is readable. And this is what the same file looks like in Excel, with a little bit of formatting. And as you can see, it's nicely arranged into organized columns of information. We have the date and time of the event, its latitude and longitude, its depth, its magnitude, and a few other fields to include when each particular entry was updated, the name of the location in which the event occurred, and the type of event. What does that mean? Well, not every event in the USGS database is an earthquake. For example, right here you can see one that's actually a quarry blast. And if we scroll through this file enough, we'll also find entries that say mining explosion and rock burst. Well, of course, these events are not earthquakes, so we can use this data field in our program to simply weed out anything that is not an earthquake. And that's what I did. Again, the first program I wrote concatenated the pieces into one large master file, but it also did a bit more. As I just mentioned, it also weeded out non-earthquake events, and it weeded out anything that had an invalid magnitude, an invalid latitude, and an invalid longitude. It also eliminated duplicate records, of which there were 18. The other criteria accounted for 1,915 records being thrown away, so we have a total of 1,933 bad records that were 86th. Last but not least, this program kept only the data fields that we need: date, time, latitude, longitude, and magnitude. That's it. That's all we need for our purposes. And this is what the end result looks like in Excel. You can see the column headers of the data fields that we kept, and if we jump down to the bottom, we see that there are 578,413 earthquakes, well over 500,000, almost 600,000, and all from January 1st, 1990, just after midnight, through June 30th, 2014, just before midnight. The next program I wrote calculated the frequencies of the earthquakes, which can be used later to calculate probabilities. At any rate, this program calculated the frequencies of all earthquakes in general, as well as many other sets of frequencies, to include each magnitude at each latitude and longitude combination, and each magnitude and above at each latitude and longitude combination. This is the one that we need the most. So I've got all the frequency data that I could possibly need. Another program that I wrote used this latitude and longitude frequency information to generate spreadsheets in a latitude-longitude grid, and this is the spreadsheet that shows all earthquakes from January 1st, 1990 through June 30th, 2014. Now I realize that it's difficult to see here, but in full screen you can almost see the land masses and fault lines, and most predominantly, the infamous ring of fire as depicted here. Back to our grid, which is currently centered on the prime meridian, the ring of fire is split. So let's center the grid on the anti-meridian. And there it is, the ring of fire. Now let's flip it back and forth a bit. And if we get a little creative, we can find ourselves a flat image of the Earth, adjust it to fit our grid, grayscale it, add the latitude longitude labels, and then drop our grid right on top of it. And there you go. The fault lines are right where they should be. And you can even see where Hawaii is located, which is within this little cluster of earthquakes right here. Now let's flash this back and forth a bit, just to see. And then in Technicolor. Okay, back to the dry stuff. Next step, go through the Barkiller's videos and collect information. Fortunately, he was very good about documenting his video, so I was able to get the vast majority of what I needed right out of his comments. And that's what I did. I actually went through the documentation of 123 earthquake prediction videos and recorded the dates that were involved, the locations, and the magnitudes. In total, in those 123 prediction videos, there were 721 individual predictions because, in most of his videos, he's predicting an earthquake in multiple locations. Now, he doesn't say that the predicted earthquake will occur in all of the locations listed. He simply says that it will occur in at least one of the locations listed. But because there are multiple locations involved, I have to treat each location in each video as a separate prediction, and that's how we get 721 predictions. Now remember, I tossed 12 videos, so we actually end up with 111 videos in the actual analysis. And in those 12 videos that were tossed, there were 15 individual predictions, so now we're down to 706 predictions rather than 721. At any rate, then came the time-consuming part. Getting on Google Earth and collecting the latitude and longitude of each location that he mentions. In doing so, I defined 4 types of areas: a spot, a circle, a block, and a hemisphere. A spot is for a specific location, like Guam. I got the latitude and longitude of the center of Guam, and then gave that location a maximum radius of 500 miles. I figured that's pretty fair. That's a circle with a diameter of 1,000 miles, but again, we're not calling this a circle, we're calling this a spot. Maximum radius 500 miles. In addition, we can also calculate the square miles of this location, or spot, and that's easy enough, pi r squared. Now let's suppose that he's predicting an earthquake to occur in Guam over a 3-day window. When I run the program that compares the USGS data to his prediction, the program is written to track several things. It counts the number of earthquakes that occurred on each of the 3 days, the total number of earthquakes throughout all 3 days, the smallest and largest earthquakes on each day, and the smallest and largest throughout all 3 days. It also tracks the closest earthquake within the predicted location, its magnitude and distance from the center, and it tracks the largest earthquake within the predicted location, its magnitude and its distance from the center. Lastly, it also tracks the closest earthquake outside the predicted location, its magnitude and distance, and the largest earthquake outside the predicted location, its magnitude and its distance. Now in this case, for those that are outside the predicted location, I simply calculate the distance from the earthquake to the center of the spot, and then subtract the radius to get the distance from the earthquake to the boundary of the location. And by the way, I'm using the Heversine formula to calculate distances. It's a formula that allows us to calculate the distance between 2 points on a sphere given their latitude and longitude. I choose this formula because it's very accurate for points that are both near and far, unlike the spherical law of cosines, which is not very accurate when the points are close together. Believe it or not, it's also possible to use Pythagorean if we properly convert the delta lat and delta lon to miles or kilometers, but it's accurate only when the points are close together, and becomes horrifically inaccurate when the points are far apart, which of course makes sense. You can't really apply a 2-dimensional equation to a 3-dimensional object. So at any rate, we're using Heversine. So let's move on. The next area type that I defined is a circle. A circle differs from a spot in that a spot has a maximum radius of 500 miles, whereas a circle has a minimum radius of 500 miles. A circle is for a location like the Aleutian Islands. Again, I got the latitude and longitude of the center of the Aleutian Islands, and then I chose the latitude and longitude of a point that would create a circle large enough to encompass all of the Aleutian Islands. This particular circle, the Aleutian Island Circle, ended up with a radius of about 919 miles, but in the event that a circle ended up with a radius less than 500 miles, I graciously coded the program to go ahead and bump it up to 500. Again, a spot has a maximum radius of 500 miles, and a circle has a minimum radius of 500 miles. And just like with a spot, we can calculate the square miles of this location. Again, pi r squared. And for a circle, the program tracks all of the same items that it tracks for a spot. The next area type that I defined is a block. This is for an area like the Caribbean. For a block, I got the northwest latitude and longitude, and the southeast latitude and longitude, forming a rectangle that contains the location, in this case, the Caribbean. To get the square miles, we simply use the Heaviside formula to calculate the lengths of two adjacent sides of the rectangle, and then multiply those two lengths together. In addition, we can use the delta lat and delta lon to calculate the latitude and longitude of the center of the block. Southern latitude plus half the delta lat is the center latitude, and western longitude plus half the delta lon is the center longitude. And once again, the program will track all of the items that it tracks for spots and circles, but calculating the distances of earthquakes that are outside a block is a little different. If an earthquake is positioned as shown here, then we calculate the distance to the closest border. If an earthquake is positioned as shown here, then we calculate the distance to the closest corner. Both approaches ensure that we always get the shortest distance. Again, the goal is to be fair. Finally, the last area type that I defined is a hemisphere, simply because there are a couple of occasions in which the bar killer is predicting an earthquake to occur within the northern hemisphere. So I define the hemisphere area type, and once again, it's possible to calculate the square miles, and in this case, that would be half the surface area of the Earth. Now, in the case of the northern hemisphere, the center of the location really doesn't have much meaning, since the center is the North Pole. Therefore, the so-called closest earthquake within the predicted area would be the one closest to the North Pole, and the distance of the largest earthquake within the predicted area would also be calculated from the North Pole. Also, in the case of the northern hemisphere, the distance of the closest and largest earthquakes outside the predicted area, i.e. earthquakes occurring in the southern hemisphere, would be the distance to the equator. Now, we hadn't made a prediction for an earthquake in the southern, eastern, or western hemispheres, but I wrote the program to handle such predictions anyway. And, of course, the center of the southern hemisphere would be the South Pole, while the center of the eastern hemisphere would be latitude 0, longitude 90, and the center of the western hemisphere would be latitude 0, longitude minus 90. For the southern hemisphere, the distances of the closest and largest earthquakes inside the predicted area would be the distance to the South Pole, and like the northern hemisphere, the distance of the closest and largest earthquakes outside the area would be the distance to the equator. For the eastern and western hemispheres, the distances of the closest and largest earthquakes outside the predicted area would be the distance to the closest meridian. In some cases, the bar killer didn't specify a particular magnitude, but instead used words like small, large, and significant. Now, he didn't use the word medium, so I added it to the list, and of course I placed it between small and large. At this point, I had to determine what these words meant, numerically speaking. And if we do a little digging and follow earthquake news and reports, we find that most reports are talking about an 8.x when referring to a significant earthquake. So there we go. Significant receives the value 8, large receives the value 7, medium receives the value 6, and small receives the value 5. I then added one more, major, and gave it the value 9. Probabilities. As I stated earlier, predicting a 6.0 earthquake or above in a 4-day window is a rather weak prediction, but only if we're predicting it to occur anywhere on Earth within those 4 days. But in this analysis, we need to calculate the probability of a specific magnitude or above in a specific location, whether it's a spot, a circle, a block, or a hemisphere. And I wrote the code to do just that, based on the frequencies of each magnitude and above at each latitude and longitude combination. I also decided, arbitrarily, that anything above a 33% probability is not an impressive prediction. Just a couple more items to cover and then we'll get started with the analysis. I now have a spreadsheet that contains everything I need in regards to the Bar Killer's predictions, and this is what it looks like. I have the video number, the prediction number, the title of the video, the watch link of the video, whether or not the prediction is based on a planetary alignment, and if so, there's a Y in this field, the start and stop dates of the prediction, the number of days involved, the area name, the area type, spot, circle, block, hemisphere, the northwest and southeast latitude and longitude, and out here we have the minimum and maximum magnitudes that he's predicting. If he doesn't specify a maximum, then we simply leave it blank. Now this field, strength, is for the words small, medium, large, significant, and major, and as you can see, the actual magnitude is not filled in for those predictions that use words instead of magnitudes. But we still need a little more information, so I wrote another program that reads this file and then adds a few more data fields to it, and this spreadsheet is the result of that program. We have all the same data fields that we started with, but the program has added the center latitude and longitude of each location, the radius of each location, the square miles of each location, and two different probabilities. The first probability is the probability of an earthquake at or above the stated magnitude, within the stated number of days, anywhere on Earth. The second probability is the probability of an earthquake at or above the stated magnitude, within the stated number of days, within the stated location. And notice that the records that have words instead of magnitudes now have magnitudes in the minimum magnitude data field, so this program has done that for us as well. And as you can see, small became 5.0, and if we scroll down a ways, we'll find this group in which he said significant, and those have become 8.0, and so on. In one prediction, he said that the magnitude was unknown, so it of course remains unknown. And in other predictions, he didn't state a magnitude at all, either numerically or otherwise, so for those I simply put unstated, and of course those remained as unstated. There are also a few predictions in which he doesn't specify an area, so in those cases I simply put, again, unstated, and the area type became undefined. Last item, and then we'll start the analysis. Let's go back to the USGS data real quick, our master file of more than 500,000 earthquake records that contains only the data fields that we need. And let this image represent that master file. It contains all earthquakes from January 1st, 1990 through June 30th, 2014. And let this section represent the period of time that's covered by the 111 prediction videos that I've reviewed and analyzed. These dates range from September 13th, 2010 in video number 1 through May 11th, 2014 in video number 111. And let's pull these records out of the master file into a separate file, and let's call it file R, meaning that these USGS data records are within the range of the videos that I've analyzed. Now let's divide file R into pieces. The red pieces represent the earthquakes in file R that match the dates of the Bar Killer's predictions, and the white pieces represent the earthquakes in file R that do not match the dates of his predictions. And let's pull these records out and put them into their own files. We'll put the red ones in file M, meaning that they match his dates, and we'll put the white ones in file X, meaning that they do not match his dates. So now we've got everything we need. We have a master file of all earthquakes from the USGS website from January 1st, 1990 through June 30th, 2014. We have a file that represents the full time period of the 111 videos that I've analyzed, and we have a file of earthquakes that occurred on the dates of his predictions, and a file of earthquakes that occurred off the dates of his predictions. At this point, I think you can agree that I've been pretty fair. I've given a spot a maximum radius of 500 miles, I've given a circle a minimum radius of 500 miles with no upper limit, and of course a block is a block and a hemisphere is a hemisphere. I also created a simple little table that will translate the words small, medium, large, significant, and major into numerical values that make sense. And finally, I'm considering any earthquake at or above the predicted magnitude, within the predicted time frame, within the predicted location, to be a hit, as long as the probability is less than 33%. So I think I've been pretty fair. And thus ends the introductory part of the video. As I forewarned, it was lengthy, but it was important to explain the entire process in enough detail such that no one can say that I've been unfair, no one can say that I haven't been thorough, and no one can say that I'm cherry-picking his predictions. We have two sets of data, the USGS data and the Bark-Harrer's predictions, and the programs that I wrote simply compare those two sets of data mathematically and produce the results of those comparisons. That's all they do. Now, as the programmer, yes, it would be easy to write those programs in such a way that they produce any results that I wish to see, but I haven't done that. If I had, then someone could make that claim, challenge me, and then ultimately debunk me. Well, that's not going to happen either. So why don't we take a little break at this point? Grab yourself a little snack, use the restroom, pull on your pud, whatever. And I'll see you back here in about 3 minutes. Welcome back, and welcome to the analysis part of the video. Thanks for hanging around. We're going to jump right to business and look at prediction number 1 in video number 1. Now don't worry, we're not going to go through all 706 predictions, but at the same time we're not going to cherry pick either, and that'll make sense in a little while. So in prediction number 1, he's calling for a 6.2 to a 6.5 to occur on the date September 13th and 14th, 2010, a 2-day window, and the area at risk is Greece. So what happened on those 2 days? Well, we can find out by looking at this spreadsheet, which was generated by one of the programs that I had written. In fact, it generated a spreadsheet like this one for each of the 706 predictions. So yes, there are 706 spreadsheets like this one. So what's this one telling us? Well, in the header we see the basic information about the prediction. We've got the video number, the prediction number, the title of the video, the link for the video, the date range, the magnitude range, and then probability 1. Now remember, probability 1 in this case is the probability of a 6.2 or above in a 2-day window anywhere on Earth. Next we have the location with its latitude and longitude, the square miles of the location, and we see that I had defined Greece as a spot, and then probability 2. And again, in this case, probability 2 is the probability of a 6.2 or above in a 2-day window in this location. So let's look at the summary real quick. It's over here, and as we see, on the 13th there were a total of 50 earthquakes. On the 14th there were 45 earthquakes, grand total 95. And on the 13th there were 13 earthquakes that were a 2-point-something. On the 14th there were 11 that were a 2-point-something, total of 24 2-point-x earthquakes. And we see the same for the other magnitudes as well. Down here at the bottom we have a little summary of the minimums and maximums, 2x and 5x on the 13th, and 2x and 5x on the 14th, so of course overall 2x and 5x. Now let's slide over a little bit. And this table is basically the same format, but it shows each individual magnitude. And we can scroll through it and do the same thing. On the 13th there were 5 earthquakes that were a 4.0, on the 14th there were 2, total of 7, and so forth. And at the bottom we see once again that there were a total of 50 earthquakes on the 13th, 45 on the 14th, grand total again 95. And in our summary, the smallest earthquake on the 13th was a 2.5, the largest a 5.9, the 14th a 2.5 and a 5.5. Overall, the smallest earthquake over those 2 days was a 2.5 and the largest was a 5.9. So what do we know so far? Well, about all we know is that his prediction was off. He had predicted a 6.2 and the largest was a 5.9, so he was off by 0.3, and we'll talk about that a little bit later. But for the moment, was he really off by 0.3? Because at this point we don't know where this 5.9 occurred. All we know is that there was a 5.9 somewhere. So let's take a look at another spreadsheet. Once again, another program that I had written generated a spreadsheet like this one for each of the 706 predictions. So yes, once again, there are 706 spreadsheets like this one as well. And it starts out the same with the basic information about the prediction in the header. And down here we see a nice little summary. Again, 50 earthquakes on the 13th, 45 on the 14th, total of 95. Our minimums and maximums are here, 2.5 and 5.9 overall. We also see that there was one earthquake within the predicted location, in other words, one earthquake within the Greece area. So of course the closest and the largest are the same earthquake, which is a 4.1, and we see in both of these cells it was 412.81 miles from the center of Greece. Outside the predicted location there were 49 earthquakes, 50 total, 1 inside, so 49 outside. The closest outside was a 4.5 at 1,390 miles away, and the largest earthquake outside the predicted location was our 5.9 at 6,488 miles away, so he was actually off by 2.1. He had predicted a 6.2, but the largest earthquake within the predicted location was only a 4.1, so he's really off by 2.1. Now let's look at this field here. This is what we really want to look at. The L means that he got the location right. In other words, it means that there was at least one earthquake within the predicted location. If we see an M here, that means that he also got the magnitude right, or in other words, there was at least one earthquake at or above the predicted magnitude within the predicted location. We might also see an O here, and that means that he got the magnitude right, but it was outside the predicted location. If we see a 1, that means that probability 1 was below 33%, and a 2 means that probability 2 was below 33%. Now the 1 is irrelevant. It doesn't matter if it shows here or not. It makes no difference because, again, it applies to the predicted magnitude occurring anywhere on Earth within the predicted time frame. But I wanted to see when it did and didn't apply, so I wrote the program to show it when applicable. So 2 is the important one, so that's what we really need to look for in this field, is an L and an M and a 2. That's what tells us that his prediction was successful. Now if we slide back over here, we see that on the 14th there were no earthquakes within the predicted location, so of course all 45 were outside the predicted location, with the closest being a 5, the largest was a 5.5, and it was 6,562 miles away. So where was this 5.9 at almost 6,500 miles away? Well, we can find that out by looking at yet another spreadsheet, and once again, another program that I had written generated a spreadsheet like this one for each of the 706 predictions. So yes, once again, there are 706 spreadsheets like this one, but this one has some additional information in the header part. Again, we see the closest earthquake overall, which was the 4.1 at a distance of 412.81 miles from the center, and the largest earthquake overall, which again was our 5.9 at nearly 6,500 miles from the predicted location. So let's take a look at this, and what we see here is another latitude-longitude grid. The longitudes are across the top and the bottom, and the latitudes are down the left and the right. So how do we read this? Well, let's look at this spot. There were 4 earthquakes here, and the largest was a 3.5. There were 10 earthquakes here, and the largest was a 3.4. Here we have 3 earthquakes, and the largest was a 3.0, and so forth. So where was the Barkeeler's prediction? Well, it was in Greece, and Greece is over here, so we see a BC where Greece is, BC meaning Barkeeler. Now again, on these latitude-longitude grids, everything is rounded to the nearest 10 degrees, so BC is showing in 2 different blocks here. This is the 4.1. There should be a BC here, but due to the rounding it just didn't show up, but that's okay. We know where it was, we know what this is, we've already verified that. So where was that 5.9? Well, it's over here, right there, and that's at latitude -10, longitude -70. So we know that it's in the southwest quadrosphere, and we can find out where that is simply by looking at Google Earth. And here we are. So let's go to -10, -70. There we go. Now I'm going to stop the zoom, and we see that it's basically in this area here, which would be western Brazil, eastern Peru, northwestern Bolivia, and obviously we're in South America. And of course, Greece is way over here. It's right there. Now let's go back to our raw grid for just a moment so I can show you something else. I'm going to slide over to the right, and we see over here we have totals for each latitude and the minimum and maximum for each latitude. So at latitude 30 there were 17 earthquakes, the smallest a 2.7, the largest a 5.0, and so forth. And we see that our 5.9 is right here at latitude -10. And down at the bottom we have the same thing for each longitude. The totals are here, and the minimums and maximums are here. And our 5.9 is right here at longitude -70. So let's move on to prediction number 2. And again, don't worry, we're not going to go through all 706. I just want to show you a few things. His dates and magnitudes are the same for this one, so the only thing that we're going to see different in the header is the prediction number, the location, which is Japan in this case, and probability 2. Now we don't really need to look at this matrix because it contains exactly the same information that was in the matrix for prediction 1, simply because it's the same 2 dates, so everything here is going to be the same. So we'll move on to the comparison here. And we see, once again, all of this information is the same. 95 earthquakes, 2.5 was the smallest, 5.9 was the largest. But in this case, on the 13th, we've got 2 earthquakes in the predicted location, which again is Japan this time. And there were also 2 on the 14th. A 5.0 was the closest on the 13th at 338 miles. A 4.1 was the closest on the 14th at 420 miles. So the 5.0 was our closest overall. and our largest overall was a 5.8 in the Japan area. And then outside the predicted area we had 48 and 43, total of 91. Closest 50 at 39 miles, 45 at 347 miles. So the 50 was the closest overall, and of course there's our 5.9. Now we don't really need to look at the latitude-longitude grid, but we can, and everything is going to be the same except, of course, the predicted location, which is over here. This is the Japan area. Now let's look at prediction number 3 real quick. Same dates again, same magnitudes, and this time we're looking at the Philippines. But notice here, absolutely nothing happened within the Philippine area on those 2 dates. Okay, we're going to jump to prediction number 6 at this point, which is in video number 2, and this is for the Aleutian Islands. He's calling for a 6.0 over this 2-day period, which is October 5th and 6th, 2010, and I'm showing this one simply because I thought the Aleutian Island area was rather interesting. So let's take a look at the grid. There we go. And the Aleutian Island area is over here, and of course it's split by the anti-meridian, so if we slide over to the right, we'll find the rest of it over here. And if we jump to our comparison, we'll see that the largest earthquake inside the predicted area was a 4.8, the largest outside was a 5.6, and we'll go back to our grid, and that 5.6 was right here at -20, -170. So let's jump on Google Earth again real quick and we'll see where that's at. There we go. Now let's go to -20, -170. And that's going to take us, well, as we saw on the grid, basically due south of the Aleutian Islands. And here we are. That earthquake occurred pretty much due east of Fiji, which is right here, and south-southeast of Samoa. So let's jump to prediction number 51. This was in video number 10. He's calling for a 6.8 in this 5-day window from November 26, 2010 through the 30th in the Benin Islands of Japan. And let's scroll down through the matrix a little bit here and we'll see that there was indeed a 6.8. Well, that's rather exciting. So let's take a look at our comparison. And there we go. And we see that the 6.8 was indeed within the predicted location, 204 miles from the center. He predicted a 6.8, there was a 6.8, and if we slide over here to the right, we see our L, and our M, and our 2. So this was a successful prediction. And then in our grid, we can scroll over to the predicted location, and there it is. And we see a caret next to the 6.8, which means that the earthquake within the predicted location was at or above the predicted magnitude. I don't know if you can see the caret or not, but it is there. So we have verified in all of our spreadsheets that this was a successful prediction. Now we're going to jump to prediction number 651, which was in video 96. He's calling for a 7.8 in a 2-day window, August 25th and 26th, 2013, and it's for the Northern Hemisphere. And what we see is that the largest earthquake in the Northern Hemisphere was a 5.3, and the largest outside the Northern Hemisphere, in other words down in the southern, was a 5.8, and it was 2,300 miles from the equator. And in our grid we see that the entire Northern Hemisphere is filled with BCs. There they all are, and if we look just below the equator, we can see the closest ones. And there they are. There's a 4.8, a 4.4, a 4.0, another 4.8, and the largest was the 5.8, and that one was right here. So you may be wondering if I actually looked at all of these spreadsheets. 706 comparison sheets, 706 matrix sheets, 706 grid sheets, and no, I didn't, because my comparison program also generated a spreadsheet that's basically an overall summary of everything that occurred. And here's that spreadsheet. I've got the video number, the prediction number, the link to the video, the begin and end dates of the prediction period, the number of days in that window, the low end of his magnitude prediction, the high end, probability 1, the location of the prediction, and then probability 2, the number of earthquakes that occurred within the prediction window, the minimum magnitude that occurred within that window, the maximum that occurred within that window, the number of earthquakes inside the predicted location, the closest one in the predicted location and its distance from the center, the largest and its distance, the number of earthquakes outside the predicted location, the closest earthquake outside and its distance, the largest and its distance, how much he was off by, and then finally our hit indicator. And here you see there's one with an O in it, and in this case he had predicted a 6.0, and there was in fact a 6.3, but it was outside the predicted area by 6,800 miles, and in this case the predicted area was, vaguely enough, Mexico. But at any rate, there was at least one earthquake at or above the predicted magnitude, but it was outside the predicted area, so that's why we see an O in this field. Now I'm going to hide some of the columns so that we can fit this on the screen more easily. There we go. Now remember, all we really need to look for is an L and an M and a 2 in this column over here. But before we do that, let's run a couple of experiments and I'll just kind of show you what we can do with this spreadsheet. At the moment I'm going to sort it, and we'll sort it on the low end of his prediction and the prediction number, and there we go. Now this allows us to quickly locate those predictions in which his predicted magnitude was either unknown or unstated, and they'll be all the way down at the bottom. And we can see that the largest earthquake that occurred within those predictions was a 7.1. The smallest looks like it was a 5.8, so that's what happened during the periods of those particular predictions. The largest earthquakes inside the predicted areas range from 2.9 to 5.6, and the largest earthquakes outside these predicted areas range from 5.8 to 7.1. And of course over here there is no M, because we don't know what he's predicting in terms of magnitude. We have no idea. But nonetheless, the largest earthquakes that did occur within the associated areas are these right here, and they're not particularly notable, 2.9 to 5.6. So let's sort this again on some different fields, and this time we're going to sort it on how much he was off by. And there we go. On this one he was off by 0.1. Ouch! He predicted a 7.0, and the largest earthquake inside the predicted area was a 6.9, so he was off by 0.1. Oof. Well, maybe we can give him credit for that one. We'll see. We're going to talk about this a little bit. Here's a prediction for a 5.1. The largest inside the predicted area was a 4.9, so on this one he was off by 0.2. Same difference here. He predicted a 7.0. The largest inside the predicted area was a 6.8, so he's off by 0.2 again. And on this one he was off by 0.3. He predicted a 6.8, and the largest in the predicted area was a 6.5. So let's talk about this difference here a little bit. If you know how the Richter scale works, then you know that a 2.0 is 10 times stronger than a 1.0 in terms of the amount of shaking that occurs. A 3.0 is 10 times stronger than a 2.0 and therefore 100 times stronger than a 1, and a 4.0 is 10 times stronger than a 3, therefore 100 times stronger than a 2, and therefore 1,000 times stronger than a 1, and so on. So let's take a look at a graph of that, and this graph shows the range of just a single magnitude, from x.0 to x.9 plus 0.1. So it could be showing 7.0 to 8.0, whatever. It doesn't matter. But at any rate, what this shows is the strength of an earthquake at each level up the scale. So if we look at it visually, we can see that an x.3 is about twice as strong as an x.0. So do you see why I have a difficult time letting him be off by too much? 0.3 may not sound like much, but in terms of strength, a difference of a mere 0.3 is twice the strength. For example, if he predicted a 6.0 and there was a 5.7, that's only half the strength of what he predicted. So even though the magnitude difference sounds rather small, the strength difference is rather significant. And we can see that an x.6 is 4 times as strong as an x.0, an x.9 is 8 times as strong as an x.0, and of course the next 0.0 is 10 times stronger than the previous 0.0. So at any rate, this is why I have a difficult time letting him be off by too much. 0.3, I have to say, that's my limit. I don't think I can allow him to be off by more than that. That's a factor of 2 times the strength, so I think that has to be my limit. So let's go back to our spreadsheet again, and this time we're going to sort it on that hit field. And there we go. Now we can find the LM2. And we scroll, and we scroll, and look at that. 2. There were 2 predictions that were actually accurate. The 6.8 that we looked at earlier in prediction number 51, there was indeed a 6.8. And this one was a 7.0 predicted for Tonga that was in prediction number 331, and there was, in fact, a 7.3. So these are the only 2 that he got right. The only 2 out of 706. Now if we look here, look at this. Look at all of these. There was an earthquake at or above the predicted magnitude, but they were all outside the predicted location. Every one of these. That's what the O means, remember? There are a bunch of them. And here are a bunch of O's that are all by themselves, and these blank ones here are situations in which absolutely nothing of significance occurred, either inside or outside the predicted location. And there's quite a few of them. There are about 200 something, if I'm not mistaken. 238, I believe. So 238 predictions had no significant activity at all, either inside or outside the predicted locations. Zip, zero, zilch, nada, and only 2 that were actually accurate. Let's go back to the top and we'll sort it again, and we're going to sort it on the off by. And what did I say? I said we'd let him be off by 0.3, right? So that's 1, 2, 3, 4 predictions that will add to the other 2 that were actually correct. So now we've got 6 predictions that were either accurate or within our margin of error of 0.3. 6 out of 706. So what have we proven so far? Well, at the moment, about all we know is that his ability to predict earthquakes is, well, dismal at best. So when all is said and done, couldn't we have just come to this spreadsheet in the first place and avoided everything up to this point? Well, sure, but if I had done that, then there wouldn't be any understanding of where this spreadsheet came from or how it was generated. So to avoid any of those questions, I've spent a great deal of time explaining the entire process in as much detail as possible so that the source of this spreadsheet is fully understood, as well as the conclusion. His ability to predict earthquakes pretty much sucks. But we're not really done yet, are we? After all, the premise of his predictions is that there's a correlation between notable solar activity in earthquakes and planetary alignments in earthquakes. So that's what we really need to look at, isn't it? Okay, let's go back to our USGS master files, files R, M, and X. Remember those? File R is all USGS data records that fall within the dates of his predictions, starting with September 13th, 2010 in prediction number 1, through May 11th, 2014 in prediction number 706. And file M contains the records from file R that match his dates, and file X contains the records from file R that do not match his dates. So let's look at the graphs of those files. This is the graph of file R, and notice that the frequency of earthquakes is pretty much stable all the way across from left to right, despite a few spikes here and there. In other words, if there was any kind of correlation between earthquakes and external forces, then we should see the graph bottom out on the dates that don't match his predictions, right? Because what is a correlation? Well, a correlation means that if A happens, then B happens. And if A does not happen, then B does not happen. That's a correlation. But so far, that doesn't seem to be the case here. So let's look at the graph for file M, and we see, once again, the frequency of earthquakes appears to be pretty stable all the way across from left to right. And here's the graph for file X, and look at that. Pretty stable, right? But that's not even the point. If there was a correlation, then file X should be pretty much empty. There shouldn't be any data in it. In other words, what we're seeing is something that we already know. Earthquakes happen. And just because there are earthquakes that occur during periods of notable solar activity doesn't mean that there's any kind of correlation. So you might as well claim that there's a correlation between weekends and earthquakes. Are there earthquakes on the weekends? Sure there are. Are there earthquakes Monday through Friday? Sure there are. And, more importantly, there are just as many. In other words, there just isn't a correlation. So let's take it one step further. Let's go back to the file R graph, and we'll tell Excel to add a trend line. And there it is. No trend at all, up or down. And then we'll do the same thing for the file M graph. Again, no trend at all. And in fact, the trend line is in exactly the same place as the trend line in the graph for file R. Now let's do file X. And, once again, not only is there no trend, but the trend line is, once again, in exactly the same location. So there is absolutely no correlation whatsoever between earthquakes and the external forces that the bar caroler is looking at. So at this point, I can only imagine what the bar caroler might be thinking.
Do you know what this means? It means that this damn thing doesn't work at all.
Yeah, that's more or less what I was thinking, or at least words to that effect.
And I'm not trying to perpetuate fear at all.
Earthquake warning has been issued.
Thanks for watching.